Good evening, ladies and gentlemen. How is everyone doing today? I'm glad you guys are well. I'm also well, thank you. So, see, class participation is very low this evening. Is something happening tonight or tomorrow? When is the semester? I assume the semester is tomorrow. Okay. I understand this hustle and bustle, skip some classes, attend some other classes to make sure you guys have enough time to study. I know the feeling, so I completely understand. Are all of you guys also writing the semester test? Okay. So before we start off tonight's lecture, is there anything you want to know about our last night's lecture, last week's lecture? Anything I can explain? Anything you want to share? Yes, you can ask your question.
Good evening, sir.
Hi, Mr. Lavia.
Sir, I just wanted to ask, sir, between applied physicists and engineers, who is better at like just building things in general?
Oh, that is a really tricky question. It all depends on what you want to do. Because if you look at physics and engineering, there is some gray area between the two where engineers can do the job of physicists and where physicists can do the job of engineers. So the biggest question is it all depends on what label you want to work under. Um, so do you want to call yourself a physicist or do you want to call yourself an engineer? Because you think about engineering, synonym for engineering is basically applied physics. So if you look at some universities don't call their engineering degrees, they call it applied physics degrees or applied science degrees. So it all depends on what you want to label yourselves under. The general rule to these two is if you are going to industry and private sector, then most people will be engineers and most people in academia will be physicists, but there are also engineering academics, there are also physicists in practice. What a two degrees does, it gives you the appropriate background knowledge to solve complicated problems. So I hope that that's solved your, or answered your question slightly.
So basically, applied physicists and engineers can, okay, they don't do they can do sort of each other's jobs, but they also specialize in certain fields.
Yes, exactly. So also bear in mind, it's just keep in mind what you want to specialize in if you want to specialize after your undergrad degree. So it all depends where you want to specialize in. So usually specialization in these fields are postgraduate specializations. So you usually have to do a master's or doctorate to really specialize in a certain aspect, certain area, certain field, certain topic. And to get to that specialization, you need a undergraduate degree that will lead you to the correct point where you can branch off and specialize. Usually in the science domain, you can do an undergrad in physics or undergrad in engineering, and then from there on you can specialize. For example, if you have a BSc physics and honors in physics, then you can do a master's in engineering. And the other way around, if you have a undergrad in engineering, then you can do a master's in physics. And you can also combine the two, that you can have 50% engineering, 50% physics in your master's and PhD work as well. So basically the sky's the limit if you have the appropriate background.
Thank you, sir.
It's a pleasure. So does anyone else have a few questions, want to know something, want to share something with us? It's a pleasure. So to give you guys just a detail, for example, so my background is in engineering, but my speciality, where I specialize in, is in astronomy. So from master's level, things can become really interdisciplinary, and you can switch to different disciplines if you have the appropriate motivation of why you want to do it. So are there going to be any more quizzes? So yes, I'm going to schedule a quiz for next week where you will have, can complete the quiz anytime within that week. But I will put up a notification on ClickUp and all our platforms. Pleasure. So just
So
yes.
I just have one more question, sir. So do you think mining in outer space will ever become something that's viable?
Yes, I firmly believe that. And there are actually now research institutes looking at sending a some sort of a rover or probe to these asteroids and then mine it, bring back samples. But some of the biggest mining companies in the world, so now one of the biggest mining companies in South Africa are De Beers. They actually have now appointed people to start investigating asteroid mining. So these big corporations, especially mining corporations, are now investigating the possibility of asteroid mining, and some of them are really adamant to do it. The only trick is the closest asteroids, and the asteroids that has a lot of commodities we are after, are in the asteroid belt between Jupiter and Mars. So the problem is, firstly, how to get there. So that's where rocket development and space travel development needs to come in. So that so far is not the biggest problem. The biggest problem is if we get to the asteroids, how do we bring that material or enough of that material back to justify the cost of going there? And that is why there's a lot of money now being put into these privatization of space exploration. That's why Elon Musk is putting so much money in developing on SpaceX. For example, if you use a French Ariane rocket or a rocket by a rocket lab, the cost can be, and even a Soyuz rocket. So let's take Soyuz of the Russians, for example. To take a person up in space in a Soyuz, at cheapest costs $200 million per person. And that basically comes down to the weight of the person. But because Elon Musk's and SpaceX technology is reusable, Elon Musk has drop that costs down to $90 million per person. Before the end of this year, it will drop down to $60 million per person. And before the end of next year, SpaceX plans to drop that cost even down further to, they say, between $20 and $30 million per person. So space technology and to get into space is getting cheaper because there's more use for it and more industries is involved. That's why it's good that we have now we can call it a second space race, but we will have to see what's continuing in the future. So question, how will the cost drop? The cost drop because the systems we are inventing is reusable. So if you look at a Soyuz rocket, you can only fire it up and use it once. Lots of pieces burn out in the atmosphere on re-entry. Some of the first stage fall back to Earth and it's destroyed. But if you can reuse all these pieces, such as what SpaceX is doing currently, then you don't have to throw it away and you cut down costs of rebuilding it. So cost keeps dropping down. And then because there are now a competitive space industry, because Boeing also has a space exploration department and Boeing wants to be the competitor of SpaceX. Then there's Ariane, there's Rocket Lab, there's the Russian Soyuz, there's NASA that's building their new launch system, the SLS, the Space Launch System, and a few other smaller companies in the market as well. So there's going to be competitive pricing and that will also bring the costs down. Then what type of material would they mine? So in the asteroid belt there are silver, there's copper, there's gold, you get uranium, and then you get all your normal elements we can mine. There's diamonds. I know there's one asteroid in the asteroid belt that is worth, they said, something like $30 trillion worth of silver, if I'm correct. So the problem is, how the hell do you bring it back to Earth? So just a heads up for you guys, I have a really bad headache, so if I'm a bit slow tonight or make a bit of slip-ups, just correct me or tell me if I do something or misread something. So how did I determine how much it's worth? So through emission absorption lines that we talked about yesterday. So we know every element we have in the known universe, will either through electromagnetic radiation emit certain radiation at certain frequencies, and we know by using our different labs which element emits and which molecules emits at what frequencies, or it absorbs radiation, called absorption spectrums. So from these emission absorption spectrums we can determine what a composition of an asteroid is. And if we know what a composition of the asteroid is, we, for example, know how much a kilogram, how much or how big a kilogram of silver is on Earth, or a kilogram of gold. And then from there on, we can measure the size of the asteroid and then determine and interpolate how much of that element is inside that asteroid, and then we know what the cost of these materials are, and then we can calculate the value of that asteroid. Awesome. So in the lectures we had from the beginning of the semester till now, we talked about the basics of optical astronomy and radio astronomy. What are the basic characteristics of optical telescopes, radio telescopes? What are some of the objects we're looking at, and what are some of our recording and recording devices and devices we use. So from this point on, we are now getting into the fun part of this course, and we are going to discuss how everything fits together. So in this lecture, we're going to look at atoms and spectra, and how do we get spectra from atoms, a model of an atom, different kinds of atoms, electron orbits, interactions of light and matter, the excitation of atoms, radiation from a heated object, understanding spectra, chemical compositions, and then measuring the velocities, in other words, the Doppler effect. So a question, is this radiation from reflected light? So not precisely, so some of it is reflected light, but some elements emit radiation naturally that we can pick up, or absorb radiation, so absorb visible light as well, we can pick it up as well. Awake, for morning in a bell of night has flung the stone that puts the stars to flight, and lo, the hunter of the east has caught the sultan's turret and news of light. So this is just a nice quote to open up tonight's lecture. So in the previous chapter, you learned how telescopes gather light, cameras record images, and spectrographs or spectrometers spread light into spectra. So remember, spectra is the plural form of spectrum. Now you are ready to understand why astronomers make great efforts to gather and analyze spectra of the objects they study. In this lecture, we are going to answer three important questions. How do atoms interact with light to produce spectra? What are the types of spectra you can observe? What can you learn from a spectra of celestial objects? So in this image again is a small recap of our visible electromagnetic spectrum. We'll be looking at visible light, ultraviolet, and infrared. In this chapter, you'll begin using modern astrophysics, linking astronomical observations to physics observations and theories, to investigate secrets that lie beyond what you can directly see. So in this image we see here, what would that be? Any suggestions? Almost other way around. Yes, it is an emission spectrum. And this is how an emission spectrum in the visible part of the electromagnetic spectrum will look like. So here we can see our wavelength. Here we can see our intensity. So if we have our wavelength, we can convert it to frequency, and the frequency we can convert into wavelengths. So if we know what a frequency or wavelength is, we can determine the color in visible light. So here we can see this line below is the image we would receive from a spectrometer. We know what a wavelength is, then we can create this image showing this is green light, this is yellow light, and how it fits together. So this is how basically a spectrometer works, and result we will get from a spectrometer. In this chapter, you'll begin using modern astrophysics, linking astronomical observations to physics observations and theories to investigate secrets that lie beyond what you can see directly. So in this image, what is going on here? The sky is filled with beautiful and mysterious objects that lie far, far beyond your reach. In the case of the nebula NGC 2392, also called the Eskimo Nebula, about 5,000 light years beyond your reach, the only way to understand such object is by studying their light. Such analysis reveals that this object is a dying star surrounded by an expanding shell of gas it ejected a few thousand years ago. The universe is populated with brilliant stars illuminating exotic planets and fabulously beautiful clouds of glowing gas. But beyond a measure, the members of our tiny local solar system, they're all out of reach for the foreseeable future. No human space probe has visited another star, and no telescope can directly examine the insides of any celestial object. The information you can obtain about most of the universe is contained in the light and reaching you across space. So in this image right here is a good option why we use different kinds of telescopes, why we use optical telescopes and why we use radio telescopes. So these two images are the same image of the Carina Nebula. So this is how we will see the nebula in visible light. But as we can see, these clouds block the interior of the nebula. So when we look at this nebula in infrared, we can see more detail. And here we can see these red giants and red supergiants inside the nebula. So what are those clouds made of? So those clouds, we refer to those clouds as molecular clouds. So they are from the material that stars in the nebula has thrown off, and those clouds are also used to create new stars. So the most abundant element in the universe is hydrogen, so a lot of that is hydrogen, but it can also be methane, a few other molecules itself, and then some of it is just pure dust particles as well. The earthbound humans knew almost nothing about the composition of celestial objects until the early 19th century. First, the German optician Joseph von Fraunhofer studied the spectrum of the sun and discovered that it is interrupted by more than 600 dark lines, representing colors missing from the sunlight Earth receives. So question, do chemical reactions happen in these clouds? Yes, chemical reactions happen in the clouds, and you can have different molecules interact with one another to form a different molecule as well. So here we can see the electromagnetic spectrum from our own sun. So here we can see the spectral radiation intensity. So this is what per square meters per nam, and right here is our wavelengths in nanometers. So here we can see we have UV light from the sun, our visible light, but going through this we can see there are a bit of dips, so it's not continuous as the yellow graph behind suggests it should be. And these dips we see here are absorption spectrums. So we can see this is H2O, so incoming solar radiation at sea level. Yellow color shows energy absorbed by gases and air, including water vapor, carbon dioxide, ozone, other greenhouse gases, CO2, and again H2O. The other scientists performed laboratory experiments showing that those spectral lines are related to the presence of various atoms in the sun's atmosphere. Finally, astronomers observed that the spectra of other stars has similar patterns of lines, which open a window to real understanding of how the sun and stars are related. So here is just a basic understanding a model of hydrogen atoms. So here we'll have a proton, an electron, and a proton is made up of quarks. So these are two up quarks and one down quark. And then we also get the strange quark and a charm quark. So just to answer, you're going to discuss this later in your other physics courses, but you guys are familiar with the basic elements of a molecule, and for this, electron, proton, and quarks. Awesome. So now we're going to start discussing a bit more of atoms. So the atoms in stars and planets leave their fingerprints in the light they emit. By first reviewing what atoms are and then learning how they interact with light, you can understand how the spectra of objects in space are decoded. So yes, if you go to let's go back one slide, a bit off topic. Protons is made out of quarks, electrons are also made out of quarks. Then quarks can be split into smaller particles such as the Higgs boson, muons, and a few other particles. So when everything is break down to the smallest particles known, that is where string theory comes into, that the smaller particles is made out of strings. So a certain combination of strings makes the particles we already know, but that's not proven yet. So that's why there's a lot of people doing string theory. So you all probably recognize this image. This is not scientifically accurate, but most people recognize this as our basic hydrogen atom, where we have our nucleus, that's protons, neutrons, electrons. The thing about how atoms interact with light, you need a working model of an atom. In this chapter, you will begin your study of atoms by creating a mental model of an atom. Remember that such a model can have a practical value without being true. The stars are not actually attached to the spheres surrounding Earth, but to navigate a ship or point a telescope, it is useful to pretend they are. The electrons in an atom are not actually little beads orbiting the nucleus the way planets orbit the sun, but for some purpose it is useful to picture them as such. So remember in our earlier lectures where I said and discussed a model and the scientific method. So everything is coming together now. So your model atom contains a positively charged nucleus at the center, which contains two kinds of particles. Protons carry a positive electrical charge, and neutrons have no charge. That means the nucleus has a net positive charge. The nucleus of the model atom is surrounded by a cloud of electrons that are low mass particles with negative charges. So what makes the nebula hot? So it depends on what nebula we are looking at, but it's a combination of radiation and pressure. Are there atoms with positrons out there in the universe, or maybe right here on Earth? Yes, there are. So remember, a positron is the opposite of an electron. And another word for the positron is basically the nucleus of the atom, that's a proton. Normally the number of electrons equals the number of protons, and the positive and negative charges balance to produce a neutral atom. A single atom is not a massive object. A hydrogen atom, for example, has a mass of 1.67 times 10 to the power minus 27 kilograms. It's about a trillionth of a gram. Protons and neutrons have masses of almost 2,000 times greater than that of an electron. So most of the mass of an atom lies in the nucleus. An atom is mostly empty space. To see this, imagine constructing a simple scale model of a hydrogen atom. Its nucleus is a single proton with a diameter of approximately 0.00000017 nanometers, or 1.7 times 10 to the minus 15 of a meter. If you multiply this by a trillion, so 10 to the power 12, you can represent the nucleus of your model with something about 1.7 millimeters in diameter. The region of a hydrogen atom that contains the electron has a diameter of about 0.24 nanometers. Multiplying by a trillion increases diameter to about 240 meters. A common misconception. So most people, without thinking about it much, imagine that matter is solid. But now you understand that atoms are mostly empty space. The chair you sit on, the floor you walk on, are mostly not there. Have you guys thought about that thought experiment? That is actually quite interesting. If the nucleus was as big as the sun, would a solar system be bigger? Uh, what do you mean of that, Mr. Lavillo?
So, I mean, since you say that the atom is mostly space, and if you and like so if you had to scale up the atom to the size of, I mean, like to the relative, like if you can size up the nucleus to the relative size of the sun, would like the diameter of the atom be as big as the solar system, or would the solar system be much bigger?
Okay, yes, so that's actually a very good example if you can think about it. So if we have our nucleus, and the nucleus, I don't remember, I haven't done the math of this before, but let's do a thinking experiment. So if the nucleus is the size of the sun, then we will reach our first couple of electrons only where Mars and Jupiter sits in the solar system. So a bit off topic, but do you guys know who discovered the electron, proton, and neutron? Can you name them and can you tell me an interesting fact?
Yes, sir. So, Rutherford discovered the nucleus as well. Rutherford and his undergrad student, J.J. Thomson discovered.
Yes,
J.J. Thomson discovered the what the nucleus was made out of. I think he discovered the protons.
yes.
And there's this last guy. He discovered the electron. I need to. He was he was a professor in I think Cambridge, if I'm not mistaken.
Yes.
I could,
So
I
does
couldn't.
anyone want to jump in as well? So Rutherford looked at the neutron, and then his student Thomson discovered the protons and neutrons, and then Thomson's student Chadwick discovered the electrons. So it is actually quite interesting how one person's work builds on top of another person's work. And that actually happens quite a lot in the scientific world. And that's why there's a quote going around said, I'm standing on the shoulders of giants. So here we can see in this image, magnifying hydrogen atom to 10 to the power 12 makes the nucleus the size of a grape seed and diameter of the electron cloud more than 2 times larger than a US football field. There are over 100 chemical elements. The number of protons in the nucleus of an atom determines which element it is. For example, a carbon has 6 protons in its nucleus. An atom with one more proton than that is nitrogen. An atom with fewer protons is boron. Although an atom of a given element always has the same number of protons, in its nucleus the number of neutrons is less restricted. For instance, if you added a neutron to carbon nucleus, it will still be carbon, but it will be slightly heavier. Atoms that have the same number of protons but different number of neutrons are isotopes. So are you guys all familiar with isotopes and happy with the principle? Okay, so you're probably familiar with the two isotopes of carbon. So one contains 6 protons and 6 neutrons for a total of 12 particles. And it's called carbon 12. Carbon 13 has 6 protons and 7 neutrons in its nucleus. The number of electrons in an atom of a given element can vary. Protons and neutrons are bound tightly into the nucleus, but electrons are held loosely in the electron cloud. Running a comb through your hair creates a static charge by removing a few electrons from their atoms. An atom that has lost or gained one or more electrons is said to be ionized and is called an ion. A neutral carbon atom has 6 electrons that balance the positive charge of 6 protons in its nucleus. If you ionize the atom by removing one or more electrons, the atom is left with a net positive charge. Under other circumstances, an atom may capture one or more extra electrons, giving it a more negative charge than positive. Such a negatively charged atom is also considered an ion. Atoms that collide may form bonds with each other by exchanging or sharing electrons. 2 or more atoms bond together form a molecule. Atoms do collide in stars, but high temperatures causes violent collisions that are unfavorable for chemical bonding. Only in the coolest stars are the collisions gentle enough to permit the formation of chemical bonds. The presence of molecules such as titanium oxide detected in some stars is a clue that those stars are very cool compared with other stars. Electrons are bound to the atom by the attraction between their negative charge and the positive charge on the nucleus. This attraction is known as the Coulomb force. To ionize an atom, you need a certain amount of energy to pull an electron completely away from the nucleus. The energy is the electron's binding energy, the energy that holds it to the atom. The size of an electron's orbit is related to the energy that binds it to the atom. If an electron orbits close to the nucleus, it is tightly bound, and a large amount of energy is needed to pull it away. In other words, its binding energy is large. An electron orbiting farther from the nucleus is held more loosely, and less energy is needed to pull it away. That means it has small binding energy. Nature permits atoms only certain amounts or quanta of binding energy. So we usually speak of quanta of energy. The laws that describe how atoms behave are called the laws of quantum mechanics. Because atoms can have only a certain amount of binding energy, your model atom can have orbits only of certain sizes, called permitted orbits. These are like steps in a staircase. You can land on the number 1 step or the number 2 step, but not on the number 1 and 1/4 step, because there isn't one. The electron can occupy any permitted orbit, but there are no orbits in between. The arrangement of permitted orbits depends primarily on the charge of the nucleus, which in turn depends on the number of protons. So in this figure we can see an electron in an atom may occupy only certain permitted orbits, because each element has a different number of protons and therefore a different electrical charge in the nucleus attracting the electrons. Each element has a different unique pattern of permitted orbits. So in this image we can see hydrogen nuclei have just one positive charge, so the electrons' orbits are not pulled close to the nucleus. Helium nuclei have two positive charges. Only the innermost electron orbits are shown in these three examples. And then boron nuclei have 5 positive charges, so the electron orbits are tightly bound to the nucleus. So in here we can see we call the orbits, we can call them shells as well, because it creates a shell around the nucleus and it creates shells around shells. So here we can see nucleus, protons, neutrons, and electrons. So in here, these different orbits or shells, we can call them energy levels. So this is N1, N2, N3. Is everybody still following? Please interrupt me if you have any questions. So now, if you put this in a 3D model for the structure of an atom, we get something like this, putting everything together that we know. So in the green, we see our electron orbits, and then that results in a insulating magnetic field, so magnetic fields in the red. And the blue, we have our electron shells. Because remember, when we have an electron moving, that causes in return an electric field and a magnetic field. Yes, Mr. Levuyo.
So knowing that the electron moves like a wave, behaves like a wave, does it I want to say conduct does it create a magnetic field the same way as you would if you had to make what is it called an electromagnet?
Yes, it's exactly the same principle, only now on a subatomic level. So remember, when you have a wire and you put a current through the wire, a current is basically moving charged particles. If you look at charged particles, that is basically electrons. So when you have electrons moving, you have charged particles moving, and that means you have an electric field and a magnetic field.
Thank you, sir.
Pleasure. So a bit off topic. So when you look at electric, there's an entire course on, you'll probably do it in your end of your second year or in your third year. You'll do an entire course on electromagnetism. So with all the courses a university can offer in all faculties, all departments, the electromagnetism course is usually the most difficult course, but it's also at the same time the most beautiful course and wonderful course. Because it's difficult is we're working with subatomic elements, and how do you describe a electrical wave? How do you describe a magnetic wave? Because that's something you cannot physically see, so you have to use a lot of math to describe what you're working with. So it's a difficult module, but one of the most beautiful modules, if you can state it that way. And then you are all familiar with our wonderful periodic table of elements. So now we're going to start investigating the interaction of light and matter. If light and matter did not interact, you would not be able to see these worlds. In fact, it would not exist, because among other problems, photosynthesis would be impossible. So there would be no grass, wheat, bread, beef, cheeseburgers, or any other kind of food. The interaction of light and matter makes life possible, and it also makes it possible for you to understand the universe. So can you guys guess what this represents or what this is? This is the emission and absorption spectrum of our wonderful sun. Each electron orbit in an atom represents a specific amount of binding energy. So physicists commonly refer to the orbits as energy levels. So is it true that there is black light? So black light is such a crude term. I won't call it black light. You can rather say it's an absence of light, because all the visible parameters have been absorbed in some way. Using this terminology, you can say that an electron in its smallest and most tightly bound orbit is the slowest permitted energy level, which is called an atom's ground state. You can move the electron from one energy level to another by supplying enough energy to make up the difference between the two energy levels. It would be like moving a package from a low shelf to a high shelf. The greater the distance between the shelves, the more energy you would need to raise this package. The amount of energy needed to move the electron is the energy difference between the two energy levels. If you move an electron from a low energy level to a high energy level, the atom becomes an excited atom, and it moves over to an excited state. So through this course from now on, we're going to refer this as excited atoms or excited states. You're all happy with these terminology? Awesome. One way an atom can become excited is by collision. If two atoms collide, one or both may have electrons knocked into higher energy levels. This happens very commonly in hot gas, where atoms move rapidly and collide often. So question, please go through that again. So going through that again. So the lowest energy level around the atom is called the ground state. So when an electron moves from one orbit to a higher orbit, means you're going to a higher energy level, meaning the atom becomes excited, and the electron moves to an excited state. Does that help clarify things a little bit? Cool. Another way an atom can become excited is to absorb a photon. So remember, we have now, it can be by collision or by absorbing a photon. As you learned in a previous chapter, a photon is a bundle of electromagnetic waves with a specific energy. Only a photon with exactly the right amount of energy can move the electron from one level to another. If the photon has too much or too little energy, that atom cannot absorb it. So remember, we have photons from X-ray, photons from gamma rays, photons in visible light, photons in radio waves. So it's just a term we use to describe the bundle of electromagnetic waves. Because the energy of a photon depends on its wavelength, only photons of certain wavelengths can be absorbed by a given kind of atom. Yes, an atom can become unexcited. So that happens when the atom drops back to the ground state. The figure below shows the lowest 4 energy levels of the hydrogen atom, along with 3 photons the atom could absorb. The longest wavelength photons has enough energy to excite the electron to the second energy level, but the shorter wavelength photons can excite the electron to higher levels. So here we can see a hydrogen atom can absorb only those photons that move the atom's electron to one of the higher energy orbits. Here, 3 photons with different wavelengths are shown along with the charges they each would produce if the electrons orbit if they were absorbed. So here we have the nucleus, here we have our permitted energy level. So here we have our 3 coming photons. The atoms cannot exist in an excited state forever. An excited atom is unstable and must eventually, so usually within 1 times 10 to the power minus 9 to 1 times 10 to the power 6 seconds, give up the energy it has absorbed and return its electron to a lower energy level. Thus, the electron in an excited atom tends to tumble down to its lowest energy level, the ground state. When an electron drops from a higher to a lower energy level, it moves from a loosely bound level to one that is more tightly bound. The atom then has a surplus of energy. The energy difference between the levels that it can emit as a photon with a wavelength corresponding to that amount of energy. Because each type of atom or ion has a unique set of energy levels, each type absorbs and emits photons with a unique set of wavelengths. As a result, you can identify the elements in a gas by studying the characteristic wavelengths of light that are absorbed or emitted. So here we can see an atom can absorb a photon only if the photon has the correct amount of energy. The excited atom is unstable and within a fraction of a second returns to a lower energy level, re-radiating the photon in a random direction. So here we have it, you have it enough, it absorbs and it drops back and it re-radiates that energy. So you all remember these lights. What do we call these lights? And how do they work? Have you guys ever thought or read up about how these neon lights actually work? Okay, are any one of you brave enough to explain it to the class? Or would you like me to explain it? Yes, Mr. Lavuyo.
So, so is there not a wire that goes through the the tube? And in the tube, so is the tube not like a vacuum? and then as you get electricity passing through this wire, it excites the gas that's in the, no, it's not a vacuum, sorry. What's in there is a gas of a specific element, and when the electricity passes through the gas, it heats up the atom, and then the atom becomes excited, and then it releases light. And depending on the element that the gas is composed of, it'll release a certain type of light.
Yes, that's basically it. So what we have in these neon lights, so this is a tube. These tubes are filled with neon, or more precisely with this, an ionized. So remember, one electron too many or one electron too few, ionized form of neon. And then down below, we will have our plug going in. And yes, they require vacuum, so this is a vacuum tube, you can also call it that way. We provide with electricity, so this an electric current. The electric current moves through the tube. Because it's ionized, we don't need the actual physical wire going through. And then the electrons becomes excited throughout the tube. And this process of exciting electrons to higher energy levels, so higher valence orbits, and then tumbling back to the ground state, causes light to be emitted, so photons to be emitted, and that is how these lights work. I don't know if you know these normal fluorescent tubes that we use in our homes or labs or whatever, and I don't know if anyone has told you this before, but if one of them break, just stand back for a couple of minutes, because the neon or whatever gas are inside here is extremely poisonous. Yes, Mr. Bonolo.
Say, what makes the neon lights have different colors?
Okay, so what makes the neon lights have different colors? So if we go back one slide, we can see here you need a specific energy level, and at specific energy level lets the atoms jump to a higher energy level or higher valence orbit, then it tumbles back down to ground state, releasing photons. So to get the different colors of light, we know these different colors of light can be represented by different wavelengths, with different frequencies. So that meaning the input power we give it needs to create an electron to jump to a specific orbit where it tumbles down to the ground state, that it is the corresponding frequency of wavelength of the light that we want. So we play around with the energy levels of the input to make sure actually the electrons inside these tubes goes to the correct energy levels or the correct orbits, and then when it tumbles down to the correct ground state, it releases a wavelength of photon in the color we are interested in.
Oh, okay. Okay, thank you, sir.
It's a pleasure. So here we can see the excitation of electrons happens in our own sun as well. So this is a emission spectrum of the sun, and here we are looking for neon. So here we can see at a wavelength of 12 angstrom and 13.5 angstrom, we can see neon, and here we can see neon gas again in our sun. So that is why a spectrometer and spectroscopy is very important for astronomy. Yes, so it all depends on what orbit the electrons are excited to, and the energy released or the photon release corresponds to a certain wavelength and that is the light we see. So here we can see neon, here we can see neon, and here we can see another neon peak. If you look closely at the stars in the constellation Orion, my favorite constellation and object to observe, you will notice that they are all not the same color. Betelgeuse, located at the upper left corner of Orion, is quite red. Another famous star, Rigel, in the lower right corner, is blue. These differences in color arise from differences in temperature. And then you can see Orion, Orion's belt, and Orion's sword. Over there is the Orion Nebula, which is a stellar nursery that we will discuss in later lectures, where stars are born. It's one of my favorite objects to look at. So, question: so is the center of the sun really yellow, or is it solid, or maybe unknown? So the center of the sun is almost solid. Well, it is basically solid. The sun usually when it's at the end of lifetime, will have a metal core. But that is something we're also going to discuss in later lectures. So do you guys have any favorite deep sky objects you like to look or observe or read about or Google or find interesting? Booty's Void is very interesting as well. Something quite interesting seeing booties at the Hartbeespoort Hydro Observatory, where I am based most of the time. All of our servers are named after different deep space object. So our mail server is called Booties. That is something interesting. So the Booties Void is an enormous spherical region in space that contain very few galaxies, so a lot less galaxies than there would be normally in space around us. And it is in the vicinity of the constellation Bootes, and hence the name Bootes. If that answers your question a little bit. So now we're going to start looking at radiation from heated objects. The starlight that you see comes from gases that make up the visible surface of the star, its photosphere. Layers of gas deeper inside a star also emit light, but that light is reabsorbed before it can reach the surface. The gas above the photosphere is too thin to emit much light. The photosphere is the visible surface of a star because it is dense enough to emit lots of light, but transparent enough to allow that light to escape it. So when we look at it, we have our photosphere, and these arrows are convection zones that we're going to discuss later. We have radiation zones, a chromosphere around the sun, and then our corona. Stars produce their light for the same reason heated horseshoes glow in a blacksmith forge, because they are hot. If a horseshoe is not too hot, it glows ruddy red. But as it heats up, it grows brighter and yellow. But yellow hot is hotter than red hot, but not as hot as white hot. So the corona is basically the atmosphere around a sun. So yes, Mr. Groenewald, we are leading up to black body radiation. Bingo. The light from stars and from glowing horseshoes is produced by the acceleration of charged particles. Usually the accelerated particles are electrons because they are the least massive charged particles, and they are on the outside of atoms, so they are the easiest to get moving. An electron produces a surrounding electric field, and if you disturb an electron, the change in its electric field spreads outward as the speed of light as electromagnetic radiation. So I've talked about this in our previous lecture as well. But we have a electron, and then the electric wave and magnetic wave will be perpendicular to one another, so 90 degrees from one another. So if we have the electric wave moving this way, we will have our magnetic wave moving this way. So here is another representation of it. So here we can see the magnetic wave going this way. So here we can see our magnetic wave, and here we can see our electric wave. You guys still happy? Okay. The molecules and atoms in an object are in constant motion, and in a hot object they are more agitated than a cool object. You can refer to this agitation as thermal energy. If you touch an object that contains lots of thermal energy, it will feel hot as the thermal energy flows into your fingers. The flow of thermal energy is called heat. In contrast, temperature refers to the average speed of the particles. When astronomers refer to the temperature of a star, they are talking about the temperature of the gases in the photosphere, and they express those temperatures on the Kelvin temperature scale. So here we can see the Kelvin scale. So 100 degrees Celsius is 373 degrees Kelvin. 0 degrees Celsius, 270 degrees Kelvin. Absolute zero is minus 273 Celsius, and that is 0 Kelvin. Putting this all together, we have Fahrenheit, Celsius, and Kelvin. So interesting, why is the SI unit of temperature Kelvin, especially in astronomy? Any ideas, any suggestions? We can determine absolute zero without using Kelvin. So the main reason is, I don't know if you guys realize that, but you cannot say 8 degrees Celsius is twice as warm as 4 degrees Celsius. And the same with Fahrenheit. You cannot say 60 degrees Fahrenheit as twice as warm as 30 degrees Fahrenheit, because Fahrenheit and Celsius is not a linear scale, it is an exponential scale. So yes, Mr. Groenewald, the Kelvin scale is linear, so in Kelvin we can say 80 degrees Kelvin is exactly twice 40 degrees Kelvin, and that's why we use the Kelvin scale. You guys happy with that explanation? Awesome. So, in your future, especially during winter months when you have minimum temperatures of 6 to 8 degrees and maximum temperatures of 14 to 18 degrees, and someone says to you, well, the day temperature is twice as warm as the night temperature, you can call them out and say it's BS because that's not true. It's not a linear scale. Now you can understand why an hot object glows, and to put it another way, why a hot object emits photons, bundles of electromagnetic energy. The hotter an object is, the more motion there is amongst its particles. The agitated particles include electrons, collide with each other, and when electrons accelerate, change their motion, part of the energy is carried away as electromagnetic radiation. The radiation emitted by a heated object is called blackbody radiation. A perfectly opaque object would be both a perfectly efficient absorber and a perfectly efficient emitter of radiation. At room temperature, such a perfect absorber and emitter would look black, but at higher temperatures it would glow at wavelengths visible to human eye. That explains why in astronomy and physics contexts you will see the term black body referring to objects that glow brightly. So here again in this image, we can see a blue star sitting at 18,000 Kelvin will have a higher flux density. A yellow star at 6,000 Kelvin, a little bit less, and a red star will also be a little bit cooler. And that is also when we look at a flame. So for example, best will be a candle or a blowtorch. The closer you are on the source, the more bluish it will be. The further you're looking away, the redder it will be because it is already cooled down. So here we can see radiation from heated objects. So when we have 7,000 Kelvin, it will be purplish. 6,000 Kelvin, more bluish. 5,000 Kelvin, more greenish, yellowish. 4,000 Kelvin, we will have our reddish. And here we will have 3,000 Kelvin, and it continues on the wavelength. So when we are past let's say 780 nanometers, it starts going into the radio spectrum and not the visible spectrum anymore. So that is why it's important we study the entire electromagnetic spectrum. Hot objects emit blackbody radiation, but so do cold objects. Ice cubes are cold, but the temperature is higher than absolute zero, so they contain some thermal energy and must emit some blackbody radiation. So this is a thermal image of an ice cube. Everybody still following? Yes, Mr. Lavuyo.
So you can be in a room where there is like no visible light, but if you use like some sort of this type of gadget to see the thermal energy, it would be bright.
Yes, exactly. Because if we look at any object, so let's go back one slide. We know these wavelengths of about 400 nanometers to 780 nanometers forms part of the visible spectrum. So those wavelengths corresponds to frequencies in our visible spectrum. So when objects are cooler, the wavelength is longer, meaning we are moving into the radio wave spectrum. Going the other way around, when the wavelength is shorter, meaning we have a higher frequency, here we start moving in X-ray and gamma ray territories.
So hypothetically, does that mean that something can become so hot that we can't see it?
Sorry, my mic was muted there for 1 second. Can you guys hear me now? So absolute zero is the coldest possible temperature in the universe, but we can also go to the opposite spectrum, and that is called absolute hot. So that is the most hottest anything can be in the known universe. And absolute hot is 1.416 times 10 to the power 32 Kelvin.
So, and would we still be able to see objects at that temperature?
Yes, we will be able to see it because we will be able to pick up that frequency. So it will be a very, very short wavelength, meaning a very, very high frequency, but we will still be able to see it.
But not with visible light.
Not with visible light. So then we will need some sort of specialized equipment, and that will most likely be at the outermost part of gamma rays.
Thank you, sir.
So a few questions. I know absolute zero is zero, but is it possible to go below absolute zero? So no, it's not possible to go below absolute zero. If we go below absolute zero, then physics starts to break down. And then what objects are that hot? So what objects are that hot? If you go to the opposite spectrum, so if you looked at objects that emits gamma rays, and some of those objects can be quasars, and where things will also be, or were the state of absolute hot, where will be the exact moment the Big Bang occurred. So what is the highest frequency a human eye can see? Ooh, that is a good question. So that would be, if you're looking at this graph, of course I don't know the numbers, that would be something with a wavelength of 400 nanometers, I think. So yes, that's right, Mr. Garcia. C divided by 400 nanometers. So you see this picture is a representation of thermal what? So this image is just a thermal representation of black body radiation. So what types of frequencies will emit what colors? And that corresponds to the temperature of that object. So there's research being done on negative temperatures. Look for an explanation on 60 symbols on YouTube. Yes, there are research being done on it because we need to know and understand what's going on. But so far, the physics breaks down if you go below absolute zero. And then since there's no absolute zero, is there like a limit to high heat? Yes, that is what I said, absolute hot. Thanks for the calculation, Mr. Groenewald. So, the coldest gas drifting in space has a temperature only a few degrees above absolute zero, but it also emits black body radiation. Do you guys recognize this image? This is the Horseheads Nebula. So nebula have names as well. And is there a reason why there is a max temperature? Yes, there is a reason, because we want to know what absolute zero is. We want to know what the absolute maximum temperature in the universe is, meaning we can understand our electromagnetic spectrum. And if things, we can't theoretically go higher than absolute hot, because then physics also start to break down. So the maximum temperature anything was the moment the Big Bang occurred. Here is a bit better image of the Horsehead Nebula. There are two features of blackbody radiation that are very important. So firstly, the hotter an object is, the more blackbody radiation it emits. Hot objects emit more radiation because their agitated particles collide more often and more violently with each other. That's why a glowing coal from a fire emits more total energy than an ice cube of the same size. So what temperature is the Horsehead Nebula? That would be a couple of degrees Kelvin above absolute zero. The second feature of blackbody radiation is the relationship between the temperature of the object and the wavelength of the photons it emits. The wavelength of a photon emitted with a particle collides with an electron depends on the violence of the collision. For example, only a violent collision can produce a short wavelength, that meaning high energy photons, such as gamma rays and X-rays. The electrons in an object have a distribution of speeds. A few move very rapidly and a few move very slowly. But most travel at intermediate speeds. Because electrons with speeds much higher or much lower than the average speeds are rare, extremely violent and extremely gentle collisions don't occur very often. Therefore, very short wavelength and very long wavelength photon emissions are both rare. Consequently, blackbody radiation is made up of photons with a distribution of wavelengths, with medium wavelengths most common. So that is why it is important for us to study these high energy photons and low energy photons. The wavelength of maximum intensity is the wavelength at which the object emits the most intense radiation. Note that lambda max does not refer to the maximum wavelength, but to the wavelength of the maximum. Do you guys recognize this image? And what do we call this image? Or this grouping of stars? Looks like Patrick. This is called Pleiades, or its more common term, the Seven Sisters. And you actually know there's a company that uses this as their logo. So this is Pleiades, the other word is Seven Sisters, but the car manufacturing Subaru, its logo is of Pleiades. So next time you see a Subaru, you will see it's of Pleiades, so the Seven Sisters, on Afrikaans, die Sewe Sisters. It's commonly known as, but its scientific name given to it is Pleiades, and Subaru uses it. So when you look at Pleiades with the naked eye, you will see these seven brightest stars. But if you look through it in a telescope, you would see these emissions coming from these stars, and also a lot fainter stars in between. And Pleiades, it's near Orion, yes. So here we can see graphs of blackbody radiation, intensity versus wavelengths for three objects at temperatures 7,000 Kelvin, 6,000 Kelvin, 5,000 Kelvin respectively. Comparison of the graphs demonstrates that an object radiates more total energy per unit area than cooler object. So that is the Stephen-Boltzmann law. So that's another hint for the test and exam, as what is the Stephen-Boltzmann law? And that a wavelength of maximum intensity is shorter for hotter objects than for cooler objects. And remember that Wien's law. We will discuss both these laws intensely, but this little tip. And the hotter an object here would look blue to your eyes, whereas the cooler object will look red. So here we can see our lambda max, so more blue light emitted than red will give this object a bluish color, meaning our lambda max will also be higher. So here we'll see object 6000 Kelvin, only 1000 degrees lower in temperature, causes a big difference in color and total emissions, so lambda max. And then an object of 5000 Kelvin is more red light emitted than blue and gives an object a reddish color, and our lambda max will be smaller. The figure shows the intensity of radiation versus wavelength for the three objects of the different temperatures. The curves are high in the middle and low at either end because the objects emit radiation mostly intensely at intermediate wavelengths. The total area under each curve is proportional to the total energy emitted. And you can see that the hotter an object emits more total energy than the cooler objects. This rule is known as the Stephen-Boltzmann's law. A hotter object will have a shorter wavelength of maximum intensity. The figure there shows how temperature determines the color of a glowing black body. The hotter object emits more blue light than red, and this looks blue, and the cooler object emits more red than blue and consequently looks red. This is known as Wien's law. So here we can see our beautiful image of Orion again. So looking at Orion's most prominent stars and the nebula in here, we can see that they are different colors, so meaning these stars are at different temperatures, radiating different energy. But if we look at this star over here and take an X-ray image from it, we can see it's more purple because it has shorter wavelengths, this higher intensity going to the Stephen-Boltzmann's law. Everyone still following? Awesome. Objects with much cooler than stars don't glow at visible wavelengths but still produce black body radiation. For example, the human body has a temperature of 310 Kelvin and emits black body radiation mostly in the infrared part of the spectrum. And that's why we can measure our temperatures by making use of infrared cameras and infrared lasers. Infrared security cameras can detect burglars by the radiation they emit, and mosquitoes can track you down in total darkness by homing in on your infrared radiation. Although you emit lots of infrared radiation, you rarely emit high energy photons, and you almost never emit X-ray or gamma ray photon. The wavelength of maximum intensity of your glow lies in the infrared part of the spectrum. So that is how a mosquito sees us. So how would so if you would represent this as an image, how would you guys think would the image look how a mosquito sees us? So I wish we could see infrared. So if you wanted to see infrared, this is how it would look like. So another little example we are looking at. So this is another sort of calculation I can ask in the test and exam. Black body radiation is described by two simple laws that can be expressed in precise mathematical form. So many objects give off radiation as black bodies that these two laws are important principles in the analysis of light from the universe. Wien's law expresses quantitatively the relation between temperature and the wavelength at which a black body radiates the most energy. Its wavelength of maximum intensity, so lambda max, written in a form conventional intensity units, as follows. Yes, Mr. Luguio.
Sir, with the picture that you showed of, if we could see in infrared, that's what we would see. Sir, how true is that? Because those images were also like sort of made out of a representation of what visible light is to us. So how do we know that infrared would actually look like that?
So let me go back one slide. So we call this is not a true color image. This is an intensity image. So the intensity image just helps us to represent information better. So in this image, we can say the more redder or yellowish the object is, the more heat it has in the infrared spectrum. But we can change this differently. For example, inverted that more hotter things is blue and more cooler is more yellow. We can do that as well in this image, but this is called an intensity image to help us understand what we are looking at.
Thank you, sir.
Pleasure. So this formula right here is the mathematical representation of Wien's law. So that is the wavelength in nanometers of maximum radiation intensity emitted by a black body equals 2.9 million divided by the black body's temperature on the Kelvin scale. This law is a powerful aid in astronomy. For example, a cool star with a temperature of 2900 Kelvin will emit most intensely at a wavelength of 1000 nanometers, which is the near-infrared part of the spectrum. In contrast, a very hot star with a temperature of 29,000 Kelvin radiates mostly intensely at wavelengths of 100 nanometers, which is the ultraviolet. Then the Stephen-Boltzmann law relates the temperature of a black body to the total radiated energy. Energy is expressed in units called joules, so symbolized by the capital letter J. The energy of motion of an apple hitting the floor after falling from a table is about 1 joule. The total radiation in units of joules per second given off by 1 square meter of surface of an object equals temperature raised to the 4th power multiplied by a constant number, represented by the Greek lowercase sigma, multiplied by the temperature raised to the 4th power. So E equals sigma T to the power 4. So how does this help you understand stars? Suppose a star, the same size as the sun, has a surface temperature twice as hot as the sun's surface. Then each square meter of that star radiates not just twice as much energy, but 2 to the power 4 or 16 times as much energy. From this law, you can see that a small difference in temperature between two stars can produce a large difference in the amount of energy emitted from the star's surfaces. So this is straightforward, plug and play, everybody understands. Awesome. So yeah, we're going to look at how we interpret and understand spectra. So science is a way of understanding nature, and the spectrum of a star can tell you a great deal about the star's temperature, motion, and composition. The spectrum of a star is formed as light passes outward through the gases near its surface. So these are how spectra will look like of hydrogen, helium, lithium, oxygen, carbon, nitrogen. So you can see nice emission spectrums. There are three important aspects of spectra. There are three kinds of spectra. So one, continuous spectra, second, absorption or dark line spectra, which contains absorption lines, and thirdly, emission or bright line spectra, which contain emission lines. These kinds of spectra are described by Kirchhoff's laws. When you see one of these kinds of spectra, you can recognize the arrangement of matter that emitted the light. Photons are emitted or absorbed when an electron in an atom makes a transition from one energy level to another. The wavelengths of the photons depend on the energy differences between the two levels. So each spectral line represents not one energy level, but rather an electron jump between two energy levels. Hydrogen atoms can produce many spectral lines that are grouped in a series such as the Lyman, Balmer, and Parsons series. Only 3 hydrogen lines are all in the Balmer series, are visible to human eyes. The emitted photons coming from a hot cloud of hydrogen gas have the same wavelengths as photons observed by hydrogen atoms in the gases of a star. Most modern astronomy books display spectra as graphs of intensity versus wavelength. Be sure to recognize the connection between dark absorption lines, bright emission lines, and dips and peaks in the graphed spectra. The spectrum of a star is an absorption spectrum. The denser layers of the photosphere emit blackbody radiation. Gases in the atmosphere of the star absorb their specific wavelengths and form dark absorption lines in the spectra. In 1859, long before scientists understood atoms and electron energy levels, the German scientist Gustav Kirchhoff formulated 3 rules, now known as Kirchhoff laws, describing the 3 types of spectra. So remember this for tests and exams. So we first have the continuous spectrum, that is law 1. A solid, liquid, or dense gas excited to emit light will radiate at all wavelengths and thus produce a continuous spectrum. Law 2, the emission spectrum. A low density gas excited to emit light will do so at specific wavelengths and thus produce an emission spectrum. Then law 3, the absorption spectrum. If light comprising a continuous spectrum passes through a cool low density gas, the result will be an absorption spectrum. You guys happy with these definitions? Awesome. So see here, what are those vertical lines? So are you meaning vertical lines such as these vertical lines? Those are absorption spectrums. Electrons orbit the hydrogen atom are shown here as energy levels. When an electron makes a transition from one orbit to another, this means that the energy stored in the atom has changed. In this diagram, arrows pointed inwards toward the nucleus represent transitions that result in the emission of a photon. If the arrows pointed outward, they would represent transitions that result in the absorption of a photon. Long arrows represent large amounts of energy and corresponding short wavelengths, photos. Then 2a, transitions in the hydrogen atom can be grouped into series, the Lyman series, Balmer series, and Parsons series, and so on, named after scientists who carefully investigated the spectra of hydrogen atoms transition, and resulting spectral lines are identified by Greek letters. Only the first few transitions in the first series are shown. I'm going to show that to you now by going back to the second law. So the second law is the emission spectrum. So we have a low density gas excited to emit light will do so at specific wavelengths and thus produce an emission spectrum. So when we have a low intensity gas and our electrons jump to a higher orbit, meaning they become excited, they will produce photons and will be an emission spectrum. In this drawing to the right of the hydrogen spectrum, emission lines in the infrared and ultraviolet are shown as gray. Only the first 3 lines of the Balmer series are visible to human eyes. Excited clouds of gas in space emit light at all of the Balmer wavelengths, but you see only red, blue and violet photons bending to create the purple-pink color typical of ionized hydrogen. Modern astronomers rarely work with spectra in the form of images of bands of light. Spectra are usually recorded digitally, so it's easy to represent them as graphs of intensity versus wavelength here. The artwork above the graph suggests the appearance of stellar spectra. The graph at right reveals details not otherwise visible and allows comparison of relative intensities. Notice that dark absorption lines and the spectrum appear as dips in the intensity graph. So this is usually what we will see the data coming from our telescopes. The sun's spectrum at this visual wavelengths, the bright colored background shows the continuous spectrum of blackbody emissions from the sun's photosphere. The dark spectral absorption lines represent precise colors, so photons of exact energies, removed from the sun's radiation by atoms in its transparent atmosphere. Then in image B, a model of the visual wavelength emissions of bright line spectrum of NGC 2392, the nebula pictured in the chapter opening photo. So if you look at textbooks, you will see it. The emission lines from ionized atoms of hydrogen red, nitrogen red, and oxygen green, among others, are seen. Then in graph number C, graphs of near-infrared spectrum of the atmosphere and surface of Saturn's moon Titan, measured by the hydrogen's probe at an altitude of 20 meters, using light source on the bottom of the probe. So now we need to understand the spectra going forward. But I see we are almost out of time for this lecture. We have about 5 minutes remaining. So let's call this a night. We will continue this lecture on Monday evening. There's not much left for this lecture. Then we'll also start the next lecture. If you have any questions, I will gladly try my best to explain it to you. Otherwise, you guys are more than welcome to log off and have a great evening. Good luck with your test tomorrow, and good luck with everything else happening the rest of this week. Thanks, guys.
Professor,
Yes.
I wanted to ask, for practice problems, is the ones in the textbook sufficient for our semester tests and exam?
Yes, they will be sufficient. The only thing I will do with the tests and exams, I will just change the numbers a little bit.
Oh, so then most of our exams are just going to be calculations, or do we have a lot of theory that we're going to use as well?
I would say 80% of the tests and exams will be theory.
Oh, okay, cool. Thank you.
Pleasure.
So I have a question, sir.
Yes, Mr. Luyo.
So I'm sure you're aware of stars that expand and then contract over time, right?
Yes.
So in chemistry, we learned that a gas can do work on its surroundings. So is it the same for a star, like when it expands and then contracts, or like those kind of energy exchanges don't happen because space is a vacuum?
No, that is exactly what happens. So in later chapters, we will learn when stars, which remember it's a nuclear reaction. So we have two types of nuclear reaction. We have fission and fusion. Fission is what we use here on Earth. We split an atom and that releases a lot of energy. In stars, it's the other way around. We fuse two atoms and that creates a lot of energy. So the size of a star is determined by a few things. It's determined by its temperature, its pressure, but also the element it is currently fusing. So when we are fusing certain elements, the physical size of the star becomes bigger. And when it's the end of its life cycle, it collapses on itself and it will shrink a little bit again. But yes, everything comes down to chemistry and convection.
Thank you, sir.
It's a pleasure. So question, why is intensity and wavelength inversely proportional to each other? So it comes down to frequency and wavelengths are inversely proportional to one another. And frequency and intensity is proportional to one another. So usually the higher the frequency, the higher the intensity as well. The lower the frequency, the lower the intensity as well. So I think that is where a bit of a misconception comes in place. Because astronomy is an old career or old science, traditionally everything got stuck with wavelength. I'm one of the astronomers, I don't use wavelength, I use frequency. But it's easy to convert between frequency and wavelength, if that answers your question. Yes, Mr. Garcia.
I would just like to ask, because what I remember from high school about energy levels and the atom is we have like a little circle around the atom, and the electron jumps between two energy levels. And what I want to ask is, how do we reconcile the idea of energy levels in that sense and the idea of a probability space to find an electron?
Okay, I understand what you mean. So you are correct. So when you let's see if I can quickly find that slide again. That will help this a little bit. Let me just quickly see what slide number that was on. That will help explaining it. So we are looking at slide number 24. So let me go to quickly slide number 24. Come on. Let's see if there's a better way I can do this. If Blackboard Collaborates wants to give me the option to skip slides, that will be helpful. So yes, so in this slide, we can see the nucleus of our atom, and these are our energy levels or electron orbits around our nucleus. So we know with this, each element has a certain amount of protons in its nucleus and certain amounts of electrons around it. So what we're talking about in astronomy, let's take a star for example. A star is huge. And it usually starts out with hydrogen. Hydrogen gets fused into helium, helium into carbon. And because a star is so massive, there's an abundance of these elements. And because there's abundance of these elements, we know there's abundance of electrons. So therefore, we know that electrons will collide with one another. And we will see photons being emitted or absorbed. Another object we can use this is a molecular cloud in space called a maser that I discussed last night. So microwave amplification by stimulation of emitted radiation. So we have a molecular cloud, say for example, of methanol in space that's usually around a star. And then when there is a solar flare from that star or an outburst, we have now high energy particles moving through this molecular cloud. And that causes the molecular cloud to absorb certain photons moving through it. And that in return will radiate microwaves, and we can pick that up, if that answers your question.
Okay, thank you, sir.
Pleasure. So this is probably a dumb question, but if red is associated with heat because of its long wavelength, why isn't violet synonyms with cold because it has the highest frequency? So remember, the higher the frequency, the more hotter it is. So violet is more hot than red. So the higher the frequency, the hotter it is because it has a short wavelength. Awesome. So if you guys have no further questions, I'm also going to log off. So tabs are actually marked wrong. Yes, tabs are actually marked wrong. So if you think about it, in tabs, how we mark it is for us humans to understand it better. So that reference frame, it's working, but scientifically, that's basically wrong, yes. So if you have no further questions, I'm going to log off. So have a great week, everybody. Good luck with everything happening else in your other subjects. And I will see you